All right, we're going to look at the equations of motion that come out from objects in free fall. So the gravitational constant of acceleration is 9.8 meters per second squared, or 32 feet per second squared. I'm going to talk in a system that it won't matter if we're using meters per second or feet per second or meters per second squared or feet per second squared. Meters or feet will be okay. So we're going to talk about the position of an object given that we have launched it vertically from a height of from a given height. And so what happens is if we have a given height, so we're going to talk in a coordinate system. Whenever we take a function and map it to reality, we'll want to define our coordinate system. And I'm going to let my coordinate system do double work for me here as also being a graph. So this will be the function in time, and this will be the position, the height. So visually, our object's going to rise up and fall straight back down. Visually, that's what the object will do. But functionally, because we'll freeze this frame into with a time axis, and we'll see that it makes a parabola. And so if I start at an arbitrary height, that'll be s sub naught, the arbitrary height. And I'll launch it upwards with some launch velocity, v sub naught. And the positive direction of s is there, and the ground will be a height of 0. So when we put this all together, we can make a function that talks about an object under the effects of some constant acceleration due to gravity. And its position will be whatever its starting position is, plus whatever velocity we launch it with, times time, plus or not plus, if that's g, then in our system g picks up a negative sign because it's pointing downwards. So acceleration due to gravity is downwards. Then we're going to get minus 1/2 g t squared. And this equation, this equation of motion, will describe any particle or any object under the effects of a constant gravitational force or constant gravitational acceleration. So your book says a dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. So we have a big boom and we get an upward velocity of 160 feet per second. It reaches a height after t seconds, how high does the rock go? And so it says, so this is we'll need to figure out what our height is. And so we're going to use that the rock is launched from the ground, so S0, where the height at time equals 0, is 0 feet. So we can find our equation of motion. The height of our rock will be 160 feet per second times time minus our 1/2, our coefficient for constant gravity, so 16 feet per second squared times time squared. A quick unit check, time in seconds. We'll cancel seconds here. I'll get an answer in feet. Time in seconds will give me seconds squared here. That'll cancel the seconds squared down here. I'll get feet, and feet minus feet is in feet, and that will give me height. So my units do check out, which is nice. And we have our equation of motion. And so we want to know how high does the rock go? And one of the things we'll see with the equations of motion is, so the rock is going to go up to some height. We'll call this S max. And it's going to take some time for it to rise to that height and some time for it to fall back down. Should be a parabola. Bear with me, it's a parabola. This is a vertex. And we could solve this using the algebraic symmetries that we have from this, but we want our calculus to tell us why these symmetries exist and what's happening. Well, what we need to know is if my upward velocity turns to downward velocity, then at this peak, my velocity is going to equal 0. And again, notice how the graph we have, again, imagine a good parabola, laugh at my silly handwriting, that the tangent line has no slope here, or the rate of change at its maximum height is 0. I think I stood in front of you and threw a marker and said, notice when it gets to the highest point, it stops moving up and starts moving down. This is what this calculus is going to mean to us in different ways. When I reach a maximum value and I'm now turning in the other direction, my rate of change has to be 0. Well, that means if our velocity has to be 0, then our derivative, or ds dt, equals 0 at max height. So at the max of s, the derivative of s equals 0. So let's take the derivative of s prime. So I have a constant times t. So the power rule says I take my power out front. So that's 1 times 160 and bring my power down. That's t to the 0. Or I'm going to have 160 feet minus, now I'm going to take the 2 out front. All right, I'm going to use my power rule. So I'm going to get 32 feet per second times t. And so we want to know how high does it go? T seconds. So we're going to find out when this equals 0. So 0 equals 160 feet minus 32 feet per second times some time. And I'm going to leave my units out. In fact, I'm just to make it cleaner, going to write my function without the units on it. And if I take the derivative, whoops, it's 160 minus 32t. And I want to solve for t, so I'm going to, and this equals 0. So 160 equals 32t, and t equals 160 divided by 32, which is in 5 seconds. So we know it's going to take 5 seconds for it to reach its maximum height. But we also know, if we know what time is, we know what the height will be. So we have found our time of flight, and so we come back in and we plop in 5 into our function here. And so 0, 0, 800 minus 16 times 25, which is 400. So 400 feet. And so we found the maximum height this object will go under these conditions. And we basically got you the first week of physics. Now, there's a whole bunch of related kinematic equations you can get when you make the acceleration zero from the algebra that comes out of this. But the calculus is giving us ways to solve these things. All right, I'm going to pause here, and we're going to look at some economic models and biological models in the next video.